This is a video from section 12.4 and it's based off the lecture notes. If theta is the angle between vectors A and B, where theta is between 0 and pi, then the magnitude of A cross B is equal to the magnitude of A times the magnitude of B times sine of theta. Let's go ahead and take a look at the proof. Recall, A cross B is a vector, and it's a vector where the first component is the determinant of the submatrix A2, A3, B2, B3. The second component is negative the determinant of the submatrix A1, A3, B1, B3. The third component is the determinant of the submatrix A1, A2, B1, B2. And this is equal to a vector where the first component is A2, B3 minus A3, B2. This is just how you compute a 2 by 2 determinant. Notice how I took the product of the diagonals and subtracted the results. The second component is the opposite of A1, B3 minus A3, B1. And the third component is A1, B2 minus A2, B1. Now I'm going to take the magnitude of A cross B and square it. And so I'm going to square each of the components of A cross B and add the results. And so when I do, I get A2, B3 minus A3, B2 quantity squared plus A1, B3 minus A3, B1 quantity squared plus A1, B2 minus A2, B1 quantity squared. So again, I went back up to A cross B. I took the first component and squared it. I took the second component and squared it, and took the third component and squared it and added the results. And that's what I got over here. Now, this is a massive amount of algebra that I'm not going to go through, but I will tell you on the very next line here, you're going to get A1 squared plus A2 squared plus A3 squared, that quantity, times B1 squared plus B2 squared plus B3 squared. And then I subtract the quantity A1 B1 plus A2 B2 plus A3 B3 squared. Well, if you look at A1 squared plus A2 squared plus A3 squared, that's just the magnitude of A squared. B1 squared plus B2 squared plus B3 squared is the magnitude of B squared. And A1 B1 plus A2 B2 plus A3 B3, that's just the dot product of A and B, right? Remember, if you go back, A is equal to the vector A1, A2, A3. B is the vector B1, B2, B3. If I take the dot product of A and B, it's A1, B1 plus A2, B2 plus A3, B3. And that's exactly what I got here. So I get the dot product of A and B quantity squared. Now, let's go to the next page. Recall that the dot product of A and B is the magnitude of A times the magnitude of B times cosine theta. And so if I take A1 squared plus A2 squared plus A3 squared, that quantity, times B1 squared plus B2 squared plus B3 squared, minus the dot product of A and B squared, I get the magnitude of A squared times the magnitude of B squared minus the quantity, magnitude of A times the magnitude of B times cosine theta quantity squared. Now I'm going to square each factor, right? So on the next line, I get the magnitude of A squared times the magnitude of B squared minus the magnitude of A squared times the magnitude of B squared times cosine squared theta. And so I'm going to factor out a magnitude of A squared times the magnitude of B squared, And inside the parentheses, I get 1 minus cosine squared theta. But we should know that 1 minus cosine squared theta is equivalent to sine squared theta. It's an identity. And so on the last line, I get the magnitude of a squared times the magnitude of b squared times sine squared theta. We're almost done. So here we have the magnitude of a cross b squared is the magnitude of a squared times the magnitude of b squared times sine squared theta. But remember our restriction on theta. Theta is between 0 and pi, right? And that tells me that the square root of sine squared theta is equal to sine theta, right? Because if you remember, sine is non-negative in quadrants 1 and 2, right? And remember, theta is between 0 and pi, so that means you're either in quadrant 1 or 2, so I don't have to worry about absolute value bars. And so if I take the square root of both sides, that tells me the magnitude of a cross b is the magnitude of a times the magnitude of b times sine of theta. And that completes the proof. Now, two non-zero vectors a and b are parallel if a cross b equals the zero vector. So this is a consequence of the previous theorem. Now, two non-zero vectors are parallel if and only if theta is 0 or theta is pi. Right? I hope that makes sense, because if we draw a picture here, so here I'll call this B. Over here, I'll call this A, right? And remember, two vectors are the same regardless of where they are in space. And so I can bring A down so that the initial point of A and the initial point of B coincide, and I'll use red. And so A is right here, right? It's the same vector. And you notice the angle between A and B ends up being pi. But you could also have the situation where, let's suppose this is A, and I'll use black, and I'm going to draw B. Here's B. And you can see that the angle between A and B end up being 0. So two non-zero vectors are parallel if and only if theta is 0 or theta is pi. In either case, we have the magnitude of A cross B equals 0. And so therefore, A cross B is the 0 vector. And that's it. Now, let's take a look at something here. If you notice in the first drawing, I have a rectangle. And the area of the rectangle is base times height. So if you notice, I'm going to let B equal the base and H equal the height. So base times height. In the next drawing, I have a parallelogram. Okay? And so what I'm trying to do is justify something to you guys. Now, notice here we have a height, H. And I'm going to shade this triangle in red. And I claim this triangle in red is equivalent to this triangle over here in blue. Right here. And so if I just focus, and I'll highlight this in blue, if I focus on this part over here, we get a rectangle. That rectangle will give you the equivalent area of the parallelogram, and so the area still is base times height. Now, let's go to the next page. Let's take a look at a parallelogram with vectors. Suppose A and B are vectors, and suppose A and B share a common initial point that we'll put right here. And we're going to let theta be the angle between vectors A and B. Now, notice how I have a height h. That's right here. And I'm going to use a little bit of trigonometry. I'll do this over here. So if you notice, this is a right triangle. And so h divided by the length of A is equal to sine theta. And so all I'm going to do is multiply both sides by the magnitude of A, or the length of A. And remember here, I'll put this off to the side. The area is the magnitude of B, right? The length of B times the height, base times height. So if I come over here, the area is the magnitude of B times the height, but the height is the magnitude of A times sine of theta. And so, again, the area is the magnitude of B times the magnitude of A times sine of theta. So it comes directly out of the area formula for a parallelogram. And we proved, the very first theorem, we proved that that's actually equal to the magnitude of A cross B. And so the area of a parallelogram that I'm putting a star by that we absolutely have to know is the magnitude of A cross B. And that's going to conclude this video for section 12.4. And we took a look at the area of a parallelogram. We took a look at a formula for the magnitude of the cross product, among other things. So, all right. Thank you.